In this series of videos I'm attempting to repair and restore a PDP11-34A vintage computer. If you haven't seen the previous videos in this series, then what I've done so far is dismantle the system, and I've got the CPU backplane and power supply on the bench. I've got the CPU, the serial card, the console controller and the RX211 floppy disk controller inserted into the backplane. I've got the RX211 on some risers. That's currently what I'm working on. I'm trying to get the floppy drive system to work. It did initially read the floppy disks. It wouldn't boot because I think the floppy disk I had at the time was corrupt, but then it developed yet another fault. I've had a lot of faults with this machine, and currently it will not properly read the floppy disks. So what I've got here is an RX211 controller coupled to the RX02 dual floppy drive. If you're not familiar with the RX02, it's a very difficult machine to fault find on. It's got two large boards in it, and one's the interface for the drives. It provides the analog signals, stepper drivers, that sort of thing. And the other one's what's termed a CPU card. It's not really a CPU card unless you look at it in terms of the entire board being a CPU. What it really is a set of ROMs, and through various multiplexers, sequence generators and a lot of glue logic, it provides a hard-coded state machine. And there's a lot of interaction in the sort of various parts of this, but the overall design of the CPU card is intended to provide the functionality required to drive the floppy disk drives. And it provides a set of discrete functions. So although it looks like these are kind of function calls within software, they're not. These are individual hard-coded state machine processes that are within the CPU card in the floppy drive. And one of the problems you have trying to test this is it's accessed through two registers, but which data you see in those two registers depends on the current status of the state machine. So it's very difficult trying to fault find because you're kind of trying to hit a moving target, so to speak. In the previous video I was running some manual testing. You can drive the floppy disk controller manually. You just enter various values through the console, and I had a couple of comments in the previous video that I just thought I'd touch on. Perfectly valid comments, and they both said that the value I was entering for the sector was too high, and yes, I was aware of that. That was kind of the point of the test. What I was trying to do was provoke an error, and then later in the video I showed what happens when you put a valid value in. And that's an important test. What you're trying to do is figure out, can the system distinguish between valid values and incorrect values? Will it respond to them correctly? And that all gives you an idea as to where the problem might be. And the reason I'm trying to provoke, in particular trying to provoke errors, is because that's really where it's failing. The error line that's coming out of the floppy drive controller goes high at certain steps in some of the processes. So I want to see if it's valid errors or invalid. And it's not like running a piece of firmware that you can reverse engineer. This is a kind of a complex state machine that you have to try and work your way through. So that was the reason of sending invalid values. It's a valid part of the testing, and it's really the only way that you can determine if this system is working correctly. So we'll elaborate on that a bit more in this video. What I've been doing is just writing some simple test code, and while you can do some very basic testing, putting manual values in through the console, once you get beyond that, you need to really start writing a few simple test routines that you can use to more fully test the drive, the interface, and the PDP CPU itself. So up until now we've been using a very simple test program just to test the PDP CPU. and the interface card. This is just really to make sure that the console was working, the console emulator. And I said in a previous video I tend to like to get that working because it simplifies future testing. And this is specifically what I was talking about. What I've done now is written a set of test routines, and as you can see at the top, what this one does is it runs through the right sector sequence for the state machine. So in other words, it sends the expected command steps to perform that particular function. I've got two versions of this. I've got the simpler version that just runs through, doesn't check the status of the error bit. It does need to check certain bits in order to progress, because of course once you start issuing command steps to the floppy drive, because the floppy drive is a mechanical system and it's quite slow compared to the PDP CPU, the PDP CPU has to wait at various parts of the sequence for the function or the function step to complete. If you just try and run through it all in rapid succession, then essentially nothing will happen. You will always get an error. So there's the basic version, and there's also a second version that does check the error bit. And I'll just run through how this works. It's fairly simple. The steps are really writing a value to the control register on the RX211. The first one we write is just to reset the drive, just because I don't necessarily know what state it's in beforehand, and this is also a valid test step. We then check the error bit, and if the error bit is set, it jumps through to this address and the CPU, the PDP CPU will halt. Otherwise it continues, it waits for the done bit to be set, which is in the RX211 register. Assuming that works, it jumps on to the next step, which is to send the command value, in this case a value of 5. Does the same thing again, looks for the error bit. In this case it's waiting for the TR bit to be set, and it halts if there's an error, or otherwise it jumps through to the next step, which is to send the sector address. Same thing again, finally it sends the track value, and in theory, if everything worked, we should end up at the bottom here. We'll end up in the second of these two halt addresses, and we can see the address on the console once it stops, or the first one if there's an error, so I can tell whether there was an error or whether it was successful. And once I've done this, you could obviously enter this manually into the console every time you want to run the test, but it gets a bit old fairly quickly. So I turn these into text files, and that particular program is this one. And what you can then do is just send this through from the terminal directly into the RAM of the PDP CPU, and then you can run the test. And what I normally do is load up quite a few of these at the same time. I've got about 10 test programs, and I generally load them all into RAM, and I can run them in whatever sequence I want to. You can of course daisy chain these. You could have this, for example, jump onto the next test, so rather than ending here, you can just change it and jump to the start address of the next test. I also have versions of this that increment the values. So for example, the track value will increment on each pass, and at some point of course it will get too high, and that's a very good way of testing if all the bits in the controller works. Quite often you'll find that there's a single bit that's stuck somewhere and certain values don't work. But assuming it gets right through to the end of the test, then the first time it tries to write an invalid value or go to an invalid track, it halts, and you can see what the address was and how far it got. So like I said, the fault testing is as important as the valid testing, so it's something you do need to include in the testing that you're doing. So we'll go through this one. I'll show you this actually running, but all the tests are very similar. Once you've got this framework sorted out, the actual individual steps for the different instructions are quite similar. In fact, the only difference between this one and the read sector is the command code that you send. So for the read, you just send a 7 instead of a 5, but the rest of it is the same. So it's very quick and easy to get these written, and they are invaluable for testing this type of machine. The scope is set up so the blue trace is on the error line coming back out of the RX02, so we can see what the error line's doing. I've now got the floppy drive and the PDP powered up. The yellow trace on the scope is connected to the output of one of the two buffer chips on the RX02, so we can see if any data is coming out of the buffer chips. When we do the right sector test, we should see data coming out of those chips, because that's what's being used to write data onto the floppy disk. So I'll pull the terminal up into the corner of the screen. Okay, so the PDP is running. What I'm going to do now is select a program, and that will be the program we just looked at, and we'll send that through to the PDP. So as you can see, the program was sent successfully. The reason it's being sent so slowly, that's not the baud rate slowing it down, it's because each time you send the character to the PDP, it needs to process it, copy it to RAM. So if you go too fast, then in general what will happen is the PDP will crash and reset itself. So you need to set a delay between each character that you send. But now that's in memory, we can halt the PDP. We'll just check the first few bytes of the program to make sure they're correct. So it was loaded to address 1000, and we do indeed have our program. So set the PDP to the starting address. When we run this program, what will happen is it will reset the drive. It will then try to select a particular sector and track, and it will try to read it. So we'll get this started, see what happens, keep an eye on the scope. The blue trace is the error line coming back from the RX02, and the yellow line is the data that's coming out of the RX02 buffer. And as you can see, what's happened is the error line has immediately gone high. It's halted at address 1202. And if we look at our program, it's actually this one. So 1202, and you can see that the first address, as I said, if you get here, it's because there was an error. If it gets to 1204, it means that there wasn't an error. Now the reason there was an error in this case is because I have the drive door open, and as I said, this is a valid part of the testing. It needs to be able to detect that. If it's not detecting it properly, there's something wrong in the controller in the RX02. So as I say, failures are as important to test as successes. So I close the drive door. So I've got a disk in there, door's closed, and what I can do is run the program again. We should see the error line drop, which it did, and it's still low. And on top of that, we also have, we saw some data coming out of the buffer. So the address is now 1206, so it jumped to 1204, halted, and then we're seeing the next address, but it got to 1204 and halted, and as I said, that's because it jumps to 1204 if this process is successful. And so what it's done is it's gone through this, it's succeeded, it's found the sector, and by find the sector it means it's actually read the header from the floppy disk. If it can't find the correct header, then it will come back and we'll get an error, or should get an error. Now just because we're not getting an error doesn't mean it's working. It could be that we're not getting an error because the drive is faulty. What we can also do is look at the address of the interface buffer, the control register on the RX211, and notice there is no error bits. If there's an error, then the most significant bit will be set. So this would be 1 something. So it looks like that particular test was a success. As I said, this is a very good way of testing the drives themselves. You see the drive moving. You can't see it from where I am. I can just about see the lead screw on the drive, and it drives out to approximately the position that we would expect. If you want, you can obviously come in here very easily, change the values for the sector and track that we're reading, rerun the test, or as I say, I do have versions of the software that run incremental values. So run it one more time and see if we get the same result. And we do. And I've run this a number of times and I've captured the data coming out of the memory chips, and for a given sector I'm always getting the same data. So it looks like the drives are capable of reliably reading the data, and on top of that we are reliably seeing it coming out of the RAM chips when it's trying to write data, and going into the RAM chips when it's trying to read data. Sounds backwards, but that's because we're talking about the buffer on the controller card, not the RAM within the PDP. So this is what I'm doing. I'm going through the system, I'm running these test programs, I'm doing this function at a time. So I'm doing read sector testing, in-depth, write sector, empty buffer, fill buffer. And where I'm getting problems by the look of it is when it's trying to communicate between the drive and the RAM on the PDP. So this may still be a problem with the CPU on the PDP. Have found a couple of faults so far with the RX02, but none of them that would cause the problems that I'm seeing. So hopefully by the time I get to the end of all this testing, I'll have a much better idea as to where the problem lies, and then of course once I've got an idea where the problem is, I can start to focus in and track it down. So that's the approach I'm taking. I'm hoping this makes sense, and also why the invalid values are important to send when you're doing testing, just to make sure that the system is capable of recognizing that and responding in the way it's supposed to. So this is a very powerful way of testing these machines, not just for the floppy drives, but also for the other cards. You can write simple test programs. They don't take very long to write. I think this took something like 10-15 minutes, and then you can just really cut and paste this to just change the values for the other testing. So you can get some very thorough test programs written very quickly, and it's far quicker than just trying to randomly scope around looking for errors, especially on a complex system like the RX02 controller. Before I finish this video, I just want to make a point here, because I know somebody will comment on it, and I just thought I'd clarify again what I'm doing with these test programs. Usually when I show something like this, I get comments saying, why don't I use a compiler and make function calls. If you look at this, a lot of this is repeated code, so it's very bad program in terms of professional levels firmware and software. You'd normally put repetitive code like this into a subroutine or function. And the reason I don't do that in these test programs is if you make a call to a subroutine, then the CPU does some housekeeping. It pushes return address, program status word, etc. onto the stack. So firstly, you need to initialize the stack. It's not difficult, but it's an extra step. But also, when I run these programs, I want to use them in conjunction with the logic analyzer. And if you have lots of function calls, then what you end up with on the logic analyzer is a bit of a harder sequence to follow, because part of what you're looking at are the housekeeping steps made by the CPU. And it's not quite as bad with the PDPs on some systems, because a lot of the workings of the CPU are integral or internal to the CPU itself. But even so, it still has to write to the various RAM locations to save the data into the stack, and it makes it difficult or more difficult to follow the sequence through. On top of that, I want to have full control over the exact sequence of the instructions that I am writing. I don't want them being optimized or messed with. I want to make sure that the sequence is exactly as I have it here, and again that makes it much easier when I'm trying to follow through on the logic analyzer. So that's why I don't use a compiler for this sort of thing. Yes, it probably would be quicker and easier to do that, but in the long run it is far easier just to spend a few more minutes, write the code like this, so that this will give me exactly what I want when I start hooking the logic analyzer up and looking through when I get errors. So when I get an error popping up, I want the logic analyzer captured data to be as clear as possible. So that's why I don't use a compiler when I'm doing these sorts of test programs.